Oh, it says we're live. Hey guys, what's going on? Beams here. We're back. We're back. I know. Took a little bit of time off. We had our mid-project meeting with Professor Wolfram and the Wolfram Summer School team, and there was discussion. There were I don't knows. There were this is an absolutely crazy thing. Long story short, I got some good advice from Xerxes at lunch, as well as I was assigned additional reading and some homework by Professor Wolfram. I actually took the advice and did some homework and got some interesting results. I'm still not quite sure what to make of it, but we're going over the Wolfram methodology and a lot of this. Apparently, Professor Wolfram, he likes to figure things out and be like, okay, is this conceptually possible? Okay, we can have some people work. Long story short is I don't think the units page in the Wolfram Physics project has been revisited since its inception about 4 or 5 years ago. We've been taking a look, and if you take it seriously, like literally, I'm gonna show you guys. Because I mean, you can't make this stuff up, and it's one of those things every once in a while. And again, I don't know. Maybe it's just a straight up causal coincidence, but every once in a while, it's like Stephen Wolfram will conjecture something. He'll say something in a particular way, and then time goes by, and you look at something, you're like, how did he know? Again, this is hold on. Let's oh, I see they're crypto and nerdy. Oh my god, those are two of my favorite sciencey people here. Hold on. We need our warning, our thingy. Where was that? Oh god, I haven't done this in so long. Hold on. We need to cover our butts for conjecturing here. Here we go.
Although this is going to be weird, and it's going to be about a different
title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
All I know is, yes, occasionally a new kind of science, I'm like, all right, well, there seems to be 4 expressions of standard cellular automata, and then we're having the iteration of just the continual progression, iteration of time. Some may think of it almost as the tick-tock of a clock, perhaps a Turing machine modelable thing, because you can kind of model anything with a Turing machine, apparently, by magic, I guess. Okay, I'm sorry, I'm railing on, but hey, welcome, Atem. Good to see you. Dude, when I was interviewing Stephen Wolfram, I had to reach over to grab the book. It almost pulled me over. Listen, if your life is ever in danger and you don't have a big rock around, NKS may save your life. I'm not a doctor or a personal defense coach or anything. I can't falsify that. I cannot falsify Turtles on the Way Down. Yeah, exactly, nerdy. We're doing it on a MacBook Pro. We want to be honest, as transparent as we can. Okay, so let me stop bloviating, because I do actually need to finish putting together this project in like an actual like presentable deliverable form by Wednesday night. So I shouldn't be still doing research, but God, it's too much fun, and I am very ADD and get sidetracked. Okay, share full screen. Let's work on some of this right now. And then my later streams will just be me kind of cleaning them up. So this should be the only part that might be fun. Okay. It's a horrible thing to say. All right, hey, we got a Dragon Ball music in the background. All right, let's roll. Okay. So the first thing we just need to bring up is this thingy over here. Okay. Why am I showing you this random thing? Because I was assigned additional reading because I was rampantly speculating before, and I was wrong. I could tell, even as I was making my analogies, they didn't line up right. You know when you have, like, somebody makes a really good analogy, and they say, well, this is to this is to this, and you may have not considered that, and you're like, it just feels right. And again, I guess that's not a very scientific thing, although part of it's going to be the actual observation, or, no, we redefined it, the limits of basically observers like us observation. And apparently, when I was telling Professor Wolfram, it's like, I love that term, observers like us. It gives me, like, good vibes from, like, the whole PBS brought to us by viewers like you. And all of a sudden, the look on his face is like, I never thought of that. I'm like, really? It's a very prevalent meme. At least it's in my head, because I kind of grew up with that. So, okay, so the whole point here is additional reading. So rather than just staring at a lot of the same pages I have been, maybe I should actually look at the model. Okay, so this is the chapter Matter, Energy, and Gravitation from his physics project book. It's available free online. I forgot. You just Wolfram Physics Project and you can get this. Okay, so let's do some reading. In our models, not only space, but also everything in space must be represented by features of our evolving hypergraphs. There's no notion of empty space with matter in it. Instead, space itself is a dynamic construct, created and maintained by ongoing updates in the hypergraph, and what we call matter, as well as things like energy, must just correspond to features of the evolving hypergraph that somehow deviate from the background activity that we call space. Anything we directly observe must ultimately have a signature in the causal graph, and a potential. And when I asked him about it yesterday, he says, well, I am of the, to paraphrase what Professor Wolfram said, is like, well, I am now firmly in the belief that this is the way it must be. So rather than a potential hypothesis, at least Professor Wolfram, I believe his opinion is that the hypothesis about energy and momentum is that they may simply correspond to excess fluxes of causal edges in time and space. And we go over to the graph. Okay. Excess fluxes. Now, I'm not Jonathan Garrod or Stephen Wolfram. I'm not a fellow at the Wolfram Institute. I'm not going to pretend like I know all the intricacies of this. I'm like, all right, so there's going to be some crossing, some transformation, something we can identify flux. Okay. Well, Bill, here's the thing. The more I listen to some of this stuff, I'm like, I know we were talking like, it's like, I don't think there's any quote unquote one way to potentially try to interpret our realm. And the crazy thing is, a lot of this, I feel like you could reformulate in different ways. Because I know Bill has been talking about just literally take everything, like take that whole observer principle literally and be like, all right, where's your light cone go? And if you have all that entanglement, all that overlaying, I'm like, maybe you could represent it in a graph. Or, as you were saying, perhaps a distributed ledger. That seems like a very transactional way. And again, like in my head, I'm like, if you can do this for that, this for that, this for that, and it adds up, I'm like, okay, I can see how that could potentially work. Now, I might not always know how it works, but the more I learn from different people about different things, it's just, that's kind of how my brain works. It's kind of like Bill says. His goal is to like entangle different folks and ideas and everything to try to work towards something better. I'm basically of the same opinion. But my mind just kind of goes out and be like, okay, here, this. Most of it is wrong. Most everything is wrong. But every once in a while, you may hit upon something that maybe there's a little bit something there. And that's what I'm betting on. So, welcome, Nuno. It's good to see you. One of my OG friends from the Wolfram chats. Good to see you, as well as we get Jax here as well. Okay, so I'm gonna stop bloviating now because maybe I actually have some sleep and America runs on Duncan's. All right, let's get to the whole point of this. All right, so what happens if we were to take the Wolfram Physics seriously? Okay. And yes, I use Saitama for there just because I could. And I hadn't used it in a while because I need to start working out on a much more active and frequent basis again. Okay. So here's our little thing. And we are entertaining the hypothesis that now appears to be the general thought process. Well, I'm sorry. Okay. There we go. So we got that. That's our potential hypothesis. Okay. So hypothetically, let's go over here. All right. So, hold on, I need to go to the units page. Sorry, units. Okay. So basically, all right. Let's go through here. There's a term here, capital psi. It's that little. Hold on, I'll show it to you. Blah blah blah. Okay. Okay, this guy. All right. We give the relationship. Okay, so basically, if you divide h bar, or your elementary unit of action, by a unit of time, h bar is a mass times an area divided by a time. If you divide it by an additional dimensional thing of time, that means you get two time thingies in the denominator. At that point, you just have mass times two lengths divided by two times. Oh, wait. That sounds like a mass times speed squared. You kind of see where we're going with this. Yeah, because the only reason I can even conceptualize this is, one, because the Wolfram language Mathematica and Wolfram Alpha exist, and number two, I can literally just type in words rather than having to do like in college. It's like, all right, back before all this stuff. Okay, you're using a TI-83, you're plugging in all your numbers, blah 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 blah, and then you had to kind of actually, to be fair, I never even really went through any of the dimensional classes, but Wolfram Alpha keeps track of that for you. So, hence, AKA potential superpower. Okay, so what the heck is this? In effect, blah, 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 bridging energy. Okay, so this capital psi sets a scale for energies of individual causal edges in the multi-way graph. Okay, so basically, here's the thing. The interesting part is we must estimate psi. Ultimately, psi is determined by the actual evolution of the multi-way system for a particular rule, together with whatever foliation and other features define what may we describe as our experience of the universe. As a simple model, we might characterize what we observe as being generational states in the evolution of the multi-way system, as we discussed. Okay. So, that is a ratio there. I'm not saying it's pi over 2, or it might be square root of pi over 3. Not that that's the number I look for at all, but I mean, I was not expecting. I mean, again, this is speculation. It's probably nothing, but like, hold on, I need to get to the point. Okay. So the problem we ran into, full disclosure, is, all right, this is the factor that essentially we're using to define Planck units or elementary units. Okay, so the relation to this is they're estimating it that, okay, you get this K factor. Long story short is they're taking the Hubble time, aka the age of universe as far as we know, and then they're defining it by the elementary time. Long story short is if you basically take the Hubble time, you divide it by the Planck time, that's going to give you about 10 to the 61, and that's a factor that they plug in to help generate that, or at least we'll go through this a little bit here. Okay, so you get your 10 to the 61, you blah blah blah, and you're estimating that. Okay. So, but here's the question. They have all these estimates, and that's basically based upon age of universe. So they have a particular way for calculating that. And long story short is that number ends up being, was it like 10 to the 116? Yeah, something like 10 to the 116-ish around there. Where are we? Okay. Okay, so they're using that number right now. Okay. So what happens is they take the square root of that thingy, and then they multiply, they take the square root of that ginormous number, and then they just divide it into your normal Planck units to get the claimed elementary units within Wolfram physics. So example, you have the Planck time, you divide it by the square root of psi, blah, blah, blah. So it's going to be of magnitude the stuff you see down here in this little chart. Here we go. Okay. So, let's biggen this a bit. All right. So as you can see here, we got an elementary length. They're estimating using that method about 10 to the 93 meters. Elementary time, about 10 to the minus 101 meters. Elementary energy, about 10 to the minus 30 electron volts. Redonkulously small units, at least within the realms of the standard Planckian scale. Okay. So, I'm sorry. I'm not gonna take care of my chat. I'm sorry. Hold on. Let me go back. Yeah. Well, here's the thing. We should be open and transparent as much as we can. Maybe there are some things that we don't speak about for particular reasons, but that's okay. It's Nightmare Court. Yes, more Wolfram friends are here. Yes, it's yeah. Well, here's the thing. Anytime you build something, Jax, it's like you get an intuition for a lot of different stuff, and I'm learning more and more. And again, hashtag not all. But one of the things I heard from some folks here, and Bill had actually told me too, is you'll have a lot of times within different industries, you'll have folks that are very well educated, very bright young individuals. As soon as they need to do something that maybe that's more hands-on or actually fully applied to a particular thing that maybe they hadn't done in school, a lot of folks are kind of lost because they've never done it before. And sometimes it's like, okay, maybe you just want the person that can do it. Maybe you don't need the fanciest thing. You just need somebody that's interested, that's willing to work hard and do the job. I don't know. Well, nerdy, that sounds like there might be one unit to rule them all then. I'm not the Dark Lord, so I cannot say. But we will continue here. Okay. So, basically one thing, I had posited an idea, basically trying to utilize the Planck intensity as a counting measure, at least in the formulation where I was kind of going through. It was wrong. It was or some derivation of that. And even as I was explaining it, I didn't have the confidence in my own voice. So basically at lunch, Xerxes had mentioned that basically the notion of that flux through basically the hypergraph is we're considering the flux of energy and momentum, and those are ways to think about it. And I'm like, oh, I hadn't done that. Maybe I should do that. Cool. So as we can see here, based on Xerxes' idea of energy momentum having a strong meaning through our graph. And this is basically that over there, potential hypothesis. So using our standard Planckian limits, thank you for that, so to speak, we can determine our limit of Planck flux. Flux? What the flux are you talking about? I don't know. Using our previous limit of energy flux density, which is the Planck intensity, and dividing it by the limit of energy, the Planck energy, of course, because I'm a noob, we get this big number over here. That's 7.101 times 10 to the 112 inverse meters squared inverse seconds. What the heck is that? Well, at least according to Wolfram Alpha, flux. It's literally the dimension of flux, or the Schrödinger quantum mechanical probability current density, or the fluence ring. For our current discussion, I think flux is okay, because flux is something that we're kind of looking for. Okay. And then proceeding to do the naive thing and multiplying our reference ones for SI, unit of flux yields. So basically we're doing the same thing and literally just multiplying by the reference dimensions. Now, let's note, so now then we get a dimensionless number, and we can take the square root and not worry about it. Now, to be fair, this is one of the reasons why I'm here, to see if doing something like that even makes sense. However, an alternative interpretation would be, perhaps if we interpret this literally as excess fluxes, or literal flux of causal edges in time and space, we need not divide by reference dimensions? Or literally, if we're looking for flux, and we are saying that our flux through the causal edges in space and time are literally flux, well then that's kind of what we're saying anyway. And then we're basically just using the numerical representation, giving a coherent unit basis to do a count. That was a whole lot of words that I don't know are true, but I'm at least framing this. And again, this project took a much more philosophical track as well, because, well, I'm not a professional programmer. So plugging this numerical count of flux into our framework for capital psi yields, oh my god, I spelled yields wrong. Yields elementary units of the magnitude. Okay, so we have our little thingy here. So if we do this, we're just literally doing what has already been laid out by a bunch of smart folks. Okay, so elementary time, we would take the Planck time, divide it by the square root of that capital psi. So we are assuming that this could be a count of some notion of flux within our Wolfram hypergraph system. Okay, so we take the Planck length, we divide it by the square root of that, we get about 10 to the 92 meters. If we go to the ones generated, oh, according to the physics project, it looks like the elementary length is about 10 to the minus 93 meters. It's 10 to the minus 93. 10 to the minus 92. Oh, that's within an order of magnitude. If we do that for time, about 10 to the minus 100 seconds. 10 to the minus 101 seconds. Huh. Elementary energy, we take our base limit of Planckian energy. We divide it by the square root of what we are conjecturing as capital psi. About 10 to the minus 29 electron volts, 10 to the minus 30 electron volts. Seems to be within about an order of magnitude. Now again, it is an order of magnitude off, but how is this calculated? This is the mind-boggling thing. This basically was calculated as basically an estimate of the rewriting. It's based upon age of universe, so to speak, or at least within our minds. It's basically based on about, I think, 13.8 billion years or 14 billion years, and then the potential number of things there. This was calculated a completely different way. That's the thing. I'm literally just taking the Planckian limit of flux, plugging it in. I didn't know it was the... I thought it was going to be a lot less. I didn't know. I'm like, it seems to be within one magnitude. And the other interesting thing is when they're going through, where was it? Let me begin this. Because when they're going through, okay, they're dropping the numerical factors here. Because this over here, this is basically, they're kind of doing the Einstein-Kappa thingy there. Because this is that big G over C4, that's just 1 over the Planck force. So I think they're kind of trying to do the, was it the part of lambda? I don't know. I have like some other random calculations that are very naive, but I mean, the crazy thing would be if something like this, and again, have to be very skeptical, especially when you get excited. I'm like telling Xerxes, I'm getting goosebumps and stuff. It's like, it just could just be a simple numerical coincidence. If it wasn't, I'm like, how did he know? How did he literally know to look here? Because that's all I did. I literally just took the advice of smarter people. They're like, all right, do this reading. I read through. I'm like, well, that's a thing. Xerxes told me to think about it in this. I got this number. Let's put this in. And I'm like, oh, my God. And that might actually ground it in something that maybe a little less speculative. That it's what are you gonna say? There are Planck units, because that's all it is. It just was an inverse 1 over Planck length squared Planck time. That's literally flux. What are you gonna say? Oh, our Planck units are okay. Then bye bye H bar, bye bye C, bye bye all that other stuff. So it may end up being a compelling argument. And again, statistically, it is probably nothing. But we will see. Let's see. Oh, God. Nerdy's grabbing a lightsaber. What have we done? Yeah, Bill is saying that I am oh my God. I always forget energy degree of freedom for 1 unit. Okay. To be fair, that's actually making even more sense right now. See, that's why I like talking to so many folks from all over the spectrum with different ideas. Doesn't matter if I agree with them or not. It's like I might be going through something and all of a sudden someone's explaining something. I don't get a thing. And then they'll say a particular word or phrase. And then that brings me back to, I don't know, a conversation from a couple of years ago. And all of a sudden it's like, wait a second. That person that I may have thought was like barking mad may have barked or yipped some fine gem that all of a sudden starts to sparkle. And it's like in one of those like Indiana Jones movies. It's like you just take that metal gem, you put it in here, and all of a sudden all this crazy stuff happens. Door opens, and you're like, well, I was not expecting to get into the secret temple, but cool. Um, that was probably a terrible analogy. Yeah, yes, flux. It's it's something like the play. Okay. I'm trying to be restrained right here, but every once in a while, if you find some, and again, I am very biased on this. One, I happen to be a Wolfram fanboy. Two, I happen to be a member of the physics monastery. Three, I may or may not have been working on some notion of maximal extendability to try to parameterize our realm. The terrifying thing is, if I were to take many of those concepts seriously, we would probably expect something like this. Because, again, if you're going to go through, and there are many ways to try to parse our world, the Wolfram Physics Project happens to be a particular way. See, that was the thing. It's like, listen, I might not understand all these notions. Maybe I don't even agree with all of them. But just the concept of we have a new modeling tool. We have the ability to compare things from multiple different ways. Whether it's like a space-time graph, whether it's a causal graph, there is still work to be done, but I'm also putting a bit of faith, so to speak, in Professor Wolfram's intuition because it seems to be pretty good. It seems to be pretty good. And that's ultimately, if you have a way to model things, sometimes it kind of depends on literally how you slice it. With branchial graph, we're taking a slice to see basically the generational state of what's going on. Yes. Dan, hey, no, thank you, man. Thank you, my dude. Well, here's the thing. It's like, we had like a couple of classes on that, and people come from it from all different angles, and it's like, each one of those methods seems to be telling us something, or we learn a little bit of something by looking at it from a different angle. Maybe it doesn't quite get all the way that we were looking, but why wouldn't we pay attention to interesting things that come up in different facets of research? I mean, that just seems like we would want to do that, because if we're trying to figure out what's going on, and then you also need to multiply the factor of cult of personality. People are busy. People need to survive. There are all these other factors that go into stuff. And then what comes out is just the general things that we see. That's literally how I conceptualize it. It's like, we got some stuff. It's doing some things. I might not know all the stuff that's going into it. I might not know all the things that are going on. But at least I can conceptualize and put into a box, so to speak, with some stuff, doing some things, and try to figure out what's going on. Isn't that science? My dude, it's, well, here's the thing. Every once in a while, like, I was trying to make an argument, and I was completely wrong. And the good part thing is, if you actually have folks that, like, really care, if you're saying that, they'll let you know, no, that doesn't make sense. Well, at the same time, it's like, well, if we're basing it off of this in our model, and we're saying that this is going to change, this ultimately would end up changing the values of everything else. And then it's like, oh, did we run into a recursion problem? Unless maybe there is something here, and maybe there is some limit here. So, okay. So I think Okay. So, Bill, all I know is I was thinking about what you said about, was it the energy around the surface of the Earth is about about 10 to the minus 34 like joules or something, something like that. And I'm like, because I think it came up in another context, or at least something made me think about that. I'm like, I do not have time to parse through all this for this project because I literally need to at least have the bulk of it done and then just smooth it through over Monday and Tuesday. But okay, we'll do this for our last little fun stuff right now. So okay, let's go back over here. All right, so let's take a look at some other things. So we got those units there. Let's do our first thing and use the normal way that they figured this out. Okay. So over here, you got some of the Einstein equations. It's I feel so much better that it's I feel so much better that a lot of Stephen's stuff, you click on it, oh, it just brings you to a Wikipedia article. People are like, oh no, you can't do that. It's like, I mean, isn't that what a lot of people just do anyway? Like, you can find the other things there, just giving you a quick overview. If it's about something highly controversial, maybe you'd want to trust but verify, but at least a lot of science stuff, usually not too shabby. Okay, let's see where we go. Okay, so we got something like this. Let's go. I don't know. All the Greeks, yeah. We'll stick over here for now. Okay, so let's do this with the numerical. Let's do it without first. So let's just send our little inquiry. So we're gonna have big G over C raised to the 4th. Okay. So then, if we're gonna take those units, okay. So since we actually have inputs, let's plug them in. Okay, elementary energy. Okay, so we got that. Put that in there. So elementary energy. Electron volt, EV. Let's divide that by elementary length raised to the dimension. Oh, this is what they were talking about. They were to do fractal dimensions. Okay. So put that in there. I don't think that we need that many exclamation points for meters. Okay, and then that would be to the D. So okay, let's just run this for one and see what we get. So in dimension 1, I need to enable dynamics. There we go. Oh, this makes me sad. Why didn't it work? I need to put Newtonian gravitational constant. Hold on. Newtonian gravitational constant. See, this is why I use the website more myself. What? I'm like, okay. This makes me sad. You know what? In some ways, this might be a good thing because the free website seems to do just. Oh God! Wow. That would. Okay. So let's take our thick spaces out. I got that. Divide there. And we're just going to throw a big BG here, and then we should be fine. Of course. Huh. Okay. That, I guess that does make sense. Since we're doing 1, it's giving us essentially 1. Because the deviation comes at like the 5th significant digit. So 1, 2, 3, 4, 5. Okay. So that's inverse energy. So literally, if we just do dimension 1, I mean, this shouldn't be. This is just energy divided by a length. So if you do energy just divide by a length, it should give us the same thing that we would in. Okay. That's. Huh. This is. Okay, see, I just thought that was going to be 1. That, Oh! Okay, hold on. Elementary energy, so that's mass, length squared, divided by time squared. If we're dividing it by 1 length, that should give us force, right? I didn't attach any units. That's why. Okay. Okay. I was getting very confused here. I'm like, wait a second, something's wrong. Here we go. All right. Okay, I was about to say, it should come out to be force. Because if we're taking that length, because force times distance equals energy. So thereby energy divided by distance will equal a force. Okay, so now it equals 1. All right, it's 1 within our Planck units. Okay. I was getting really confused. I'm like, oh, this is an interesting thing. Why? Because I made a mistake. All right. So now, and this is inverse Planck force. Okay, so Planck force times inverse Planck force will just be Planck force divided by Planck force. We should get 1. Okay, so big G divided by C to the 4th. Enter. Okay, we get 1. There we go. Essentially 1 with a rounding error. Okay. So, that's in dimension 1. This thingy has a dimension to the other stuff. So let's do a little computational experiment. Let's try dimension 2. Okay, that changes that to, oh god, energy per area. Sunburn units. Wow. Okay, let's try dimension 3. That's where we believe we live in, and we get joules per cubic meter. That is a ginormous amount of joules. Wow. Okay. So, let's do this. Let's go back. Go back here. We get our term there. All right, now let's increase our dimension to 2. Okay. So we went from, should be 1, equivalent Planck force. So now we're getting reciprocal meters. That is, around the elementary length? That kind of looks like it, I think. Hold on. Elementary length. Okay, 10 to the minus 93. That's 10 to the minus 91. We had about 10 to the 92. That's reciprocal. So let's. That's a pretty cool number. Okay. So I have to do this because I'm a crazy person. Let's invert that thing. I want to see what that number looks like upside down. Huh. 6.074 times 10 to the 92 meters. Huh. 6.064 times 10 to the 92 meters. Huh. That's interesting. I mean, I don't think it should be that interesting because it's... As soon as we put in that proportionality factor, the square root of big psi. Again, I don't have it all. Somebody else watching at some point will probably just be like, oh, that's obvious. But right now, my thought is, well, that's just coming out from that capital psi thingy. But that's, that is at least worth a little screenshot. So let's, put that in here. Oh, God, why was this not working in my notebook? Do I need the other thingy? Maybe I just need, hold on. Let's, Okay, now it works. I'm going to assume user error. Full results. Just because I'm like, every once in a while we'll try to interpret, and sometimes the interpretations are like, So, okay. Yeah, we need to. Oh, so that's just multiplying by the Planck. Wow! Oh my God, I just realized what that does. Okay. The Planck force is deposited by Dr. Salvador Pais and mad scientist Rick DeWitt. It seems to be a proportion, or has been hypothesized as a proportionality constant to help us define size of the universe. I've done calculations. There's observational stuff that puts us within about a magnitude of that. It also seems to be the proportionality constant. Hypothetically, if we were living inside, I don't know, a black hole or something, you get the same numbers. Or at least within magnitude. So again, I don't know what's going on, but I'm trying to be less wrong. So that means we could redo all of this. So we had that. All right. So, okay, so that's the plan. Hold on. Just take this all off. Okay, all right. See, this is why I like the words. Because, yeah, you can keep track of a lot of units and stuff, especially have it here. Okay, so that gives us the Planck force. Okay. So if we just do the Planck force times that, we're going to Planck force squared, blah, blah, blah. Every once in a while, I see strings of digits and they look familiar. So we're going to get 1. Okay, essentially 1. Okay, and now we should be dividing this by the Planck force because that is the other way there. So divide it there by Planck force. Okay. Now, we're going to raise this to the second dimension. Okay, so it's giving us the inverse there. And then if we just multiply it by the Planck force, we divide the Planck force by that. Okay, that's what it is. We get some interesting results. We're going to get basically our calculated thingy. Okay. We get our calculated thingy. All right. This is why we like doing computational experiments, right? All right. So, okay. So what are we actually doing here? We are doing this little conversion. So let's put in exactly what we're doing here. Okay. And d equals 3. So this, okay. So we will do the basic thing and literally just take a screenshot, So I can throw it in my notebook. Okay, so insert. Picture from file. Reset. There we go. All right. I don't think we need that cell. There we go. All right. So what are we doing? All right. Reach curvature. Okay. So some calculations. So section. Some calculations with derived units. Derived. Okay. So more specifically gives the contribution of a single causal edge with one elementary unit of energy. Okay, so I mean, hey, we got, oh God, is it? I just realized I still had the screenshot up. That's funny. All right. So, I mean, a lot of this is kind of familiar to me just because I've been playing around for the past couple of years like a crazy person here. Okay, all right. So some calculations. So, all right. Let's add another bulleted item. Note that big G over C to the fourth is. Let me just double check. I always get I'll confuse the inverse of this. Okay. So yeah, you see big G over C4, that's just the inverse Planck force. Except when you do it that way, you need to specify. Okay, yep, Planck force, all right, is the inverse Planck force. Therefore, we can simplify with natural language our calculation to all right, so okay, so we get our elementary units of energy, blah, 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 and then force. I should probably just set these to variables and just assign them to their own units. I mean, I know how to do that. All right, wow, okay. So, hold on. We need to have this be as 1 for the first one. Okay. So, start a little thingy there. All right. It's Planck force, so that lines up. All right. So, toss out that pod. Toss out that pod. Bada boom, bada bang. I don't know. I personally like the look of the pods, and I know there's ways to make this look a lot better. I'm not always the best at that. Okay. Like 4, so we get 1. So our simplify our natural language calculation for the first, we're doing length derivative for our calculation of the First elementary length derivative. That just means we're literally just putting that to 1. It's just the first derivative. They put it there, and again, some mathematicians will probably get mad at me. It's like, it's the thing that we're dividing, that we're adjusting. Kind of like acceleration is the second time derivative because it's a length divided by time squared. Okay. Alright, so we get that unit there. Okay, so we got. Oh, jeez. Oh, I need to rewrite this. Sorry, that bothers me just how it's written. You gotta simplify things, otherwise it's. I've shown different people these calculations, and I realize it's like they'll look to be like, all right, it's the principle of massive wall of text crits you. Somebody may give you the most detailed, thoughtful response ever. It's like 7 pages long, single spaced, and you're like, massive wall of text crits you. You just don't even consume it. And at that point, it kind of becomes a waste. All right, so for the second derivative, you literally just square that thingy. Go, Wolfram Alpha. Big money, no, to interpret the traditional format only. Yes. Okay. All right. So for the second derivative, we get that. Okay, so that would be, yep, we're dividing by the Planck force there. Okay. Put our pod there. We'll get our meters term there. And this is the inverse of our calculation of the elementary length. Because we do 1 over that. Yep. Just some of these numbers are... I don't know. It's I'm just a crazy numerologist. Okay, so... Good. Alright, we got that. We got that. So, what we'll do is, okay, boom. All right, so I'll take this and then for our second derivative, the elementary length yields reciprocal meters. All right, so note that this number looks familiar. A quick inversion of it yields. So we literally just take this number, boom. Oops. Times 10 to the 91 meters raised to the -1. All right. Oh, it's a ginormous number. That's why. Okay. All right. That makes more sense now. I'm like, oh, that's kind of ginormous. All right. So we just got to convert that one over a little thingy. Okay. That. Okay. That, delete that. Okay. Boom. One over that, and then we compare it to our. Okay, bullet term. Okay. One back out. There we go. We notice that this returns. It returns approximately. Calculation for the elementary length. Six is 4, 6. Okay. Now we go to the third derivative. Sorry, I think that messes it up a little. I don't know. I like it this way. It's up to personal preference, really. What was I doing? Oh, yeah. Copy and pasting that. Blah, blah, blah. Okay, so. Okay, so what are we doing? Ah, yes. Just dividing the Planck force into this stuff. That's right. All right. Where was that? I'll divide by the Planck force. All right, third derivative. 3, let's go. Big money. No whammies. Okay. So, this should make sense because we're trying to do the whole, this is equal to 1 over length squared. Okay. Do they have it upside down? Because that means we're dividing by the Planck forces. The C4 is on the bottom. Then energy, length. Oh, it's the inverse. Okay. It's inverse. That's why I'm like, because if I take the square root of this, is going to be still reciprocal meters. It's going to be 1 over that, which will give us. Okay, so that's trivial stuff. Okay. All right. Okay. We need there. This. Yeah. When I get this thing like this, I'm like, oh my god, I don't know at all what that means. And even Wolfram Alpha at some points, once you get above like the third power, it will start like multiplying it several times, and you're like, oh my god. And if you don't pay attention, the calculation will like just blow up, and you're like, what the heck happened? Okay. cannot spell anything. I'm sorry. I'll be right there, guys. Hold on. Let me put this here. Oh my god, jeez. I need to calculate the thingy. I mean the cell. There we go. Oh, you're supposed to go there. All right. Okay, I can tell at least I'm probably making progress because I'm at least on to my second or third anime song right now. We had some Godzilla Final Wars in here in the background. All right, our third derivative of the elementary length yields. Okay. Oh, yeah, we just need to plug this in. Insert. Referring to our earlier definition. We insert picture from file, recents, that dude. All right. We find it to adhere to this adhere to this structure. I mean, basically, once you get something in there, it's just going to hold as long as it's related to something within the coherent system. Okay. Because we do 1 over this. 1 over times 10 raised to the 182 reciprocal meters. -2. All right. See, I'm just saying, I'm literally just doing the same thing you do in Minecraft or something. It's like, all right, hey, here's the thing. We need it in this structure. We need this many blocks. We need to put these things here. I don't know. Oh my god, why is it thinking so hard? This is scary. Oh my god. I broke it. Why? Hold on. All right, here we go. So we got over that. Okay, so this should be elementary length squared. Wow. Why does that number look kind of familiar? Oh, that's like the first couple of digits of Z2. Don't mind me. Yeah, so it's going to give us our standard elementary length. So, all right, we just need this pod, and there we go. Delete all that. All right. Go there. And then we square it. Taking square root of this yields our elementary length. over there. Boom. Okay, so square root 3.678 times 10 raised to the 180 minus 183 meters squared. Alright, boom. I realized I just said words and said it with not even the calculation, so, but yeah. I mean, it's basically, it is basically giving us that, or at least. Alright, so there we go. Boom. Bud. Alright, there we go. See, I mean, this is all like the juicy extra stuff that before it's like, skip over that, and every once in a while it's like, wait a second. That relationship looks suspiciously familiar. Why? That's what crazy people like me use to gain intuition. Just being overly anal and just being like, blah, blah. Sorry. I'm just rambling at this point. It's getting to be around dinner time, so I should probably take a break in a little bit, and we'll be back for at least 1 or 2 more sessions, because I need to make significant progress. Okay. Here's our elementary length. 6.6. Okay. 92. Okay. So we get back to the elementary length. So, since I'm a completely crazy person, what happens? Okay, so that goes to squared. Okay. What happens if we did a non-integer dimension? It's just the dimension of E. Negative 1 plus C. Oh. Okay, we break everything. Oh, let's add in this random thing because we can. That doesn't. Could we write everything as something plus E? Okay, I think. Okay, I just had a crazy thought. Okay, so how about this? Meters divide by Planck length. How about let's put E in there. Why? Because we can. Maybe I might do elementary charge. I don't know. If I just put a Euler's constant there. Well, that doesn't make any sense. Wait, what the heck just happened? Hold on, wait. Oh, okay. Oh my. Hold on. I'm sorry. I thought that for a second there that was the golden ratio. I'm just like, wait, no, I just kind of reversed one of the digits. Hold on, sorry. I was just like, okay, it's not. Okay. I'm sorry. It just something popped up, and I'm like, wait a second. I saw like the first couple of digits that seemed to be about the same. So this Planck length is 1.616. Yeah. Okay. I was like, oh, that would have been really weird. Euler's number C, it just enacted the dimensions. Okay, all right, sorry. Let's save, file. Save this flux. 6, 7, 5, 20, 25. File save. Oh no. Save the cloud. I know. Okay. So we should. Actually, to be fair, I kind of meant to do something else too. Let's. We'll save that. We'll save that for after dinner. Okay. Let's see what folks are saying. I'm sorry. I'm so bad. Trying to figure out all the other stuff and things. Okay. Oh, sorry, I have to go back. I also need to recaffeinate. Let's see, what else do we have here? Oh, it's something to do with knots rather than strings. Well, I am very biased on that. Coincidentally, dimension 3 is the only dimension where knots make sense. The universe is a multiple choice. Well, it may or may not promote fairness or something like that. Let's see. Yeah, no, that's... See, Bill, that's the thing. I listen to folks, and it's like, 5-dimensional ADS-CFT CFT corresponds. What does that mean? It means that we can know everything that's going on within a black hole, so to speak, by knowing what's going on at the surface. It's like, oh my God, that's mind-blowing. And to be fair, that is kind of mind-blowing. And then occasionally I could be completely wrong. Maybe my mind was just filling in the blanks. It probably was. I could have sworn I've come across some old Professor Feynman lectures from, I think, like maybe the 60s or 70s. And at one point, I'm pretty sure he's like, well, if you had a bubble or a sphere, if you can tell what's going on within the surface of that sphere, you can tell everything that's going on inside. And I'm like, maybe that's fundamentally different for a black hole. I mean, I could imagine that would be different because it seems to be a very different type of thing as far as we believe we understand. But then at the same time, I'm like, well, what if that's just a general thing? I'm like, well, if Professor Feynman like 60 years ago was like, oh, if you can tell everything that's going on at the surface, you can tell everything that's going on the inside. Why? I don't know, entropy? And then it's like, oh my God, one of the most cited papers ever. And again, nothing against Professor Maldacena. I'm sure it's beautiful, but I'm like, I'm sure there's a mathematical difference, but I'm like, isn't the concept like, if you can tell what's going on, basically if you have the surface area nailed down, you can tell everything. So like, if he said that 60 years ago, should we really be that surprised? I don't know. See, that's the thing. You got to realize once everybody is different, and once everybody's different, it's like you have a multitude of it. I mean, that's kind of, I think, why they say diversity is the spice of life. Now, again, I'm at the Wolfram Summer School, and even Professor Wolfram's like, I eat the same thing for breakfast every day. I can't criticize him, because a lot of times I will do the exact same thing. So, it's, hey. Tick-tock goes the clock. Okay. I occasionally will listen to some of those things. I try to stay away from a lot of this. My thing is, I don't want to be talking about things that I may or may not need a security clearance for. So, as far as I'm concerned, I'll occasionally listen, but I'm like, I don't spend too much time thinking about it because I'm like, I'm looking for just some of the basic stuff, and I'm just gonna say Occam's razor. I'll leave it at that. Okay. Incompleteness. Well, that's the thing. Is the journey ever truly complete? For F equals ma, that's the thing. It's like I have a much greater appreciation for that now, because that's one of those things you hear. I think a lot of people have heard it. If you've heard E equals MC squared, MC hammer, or whatever, it's like, you may have heard F equals ma. It's, if you've taken some science classes, probably heard it, but now it's like, oh my God, I can actually start to appreciate that now, because now I can try to even start to verbalize what's actually going on. Mostly taught to me by folks like you, folks that have sat down with me, spent time, put up with my obnoxious butt, whether it was Jonathan, Professor Wolfram, Thad, Rick, a lot of y'all in the chat, Bill, and everybody, yeah. Or Snacks. Oh God, Snacks has had to deal with me. Jeez. I'm sorry, man. I literally just take it literally nerdy. I'm just like, that's just the maximum force. I take them as limits. Now, a lot of people think, they're the minimum limits because something quantum mechanics. It's like, yeah, sure, but it's like, what about the Planck energy? Well, that's like the energy in a lightning bolt. I'm pretty sure at least some particle physicists would say that is not a minimal energy. Now, as a limit, I would say it's a maximum energy. That's why I think of them as limits or perhaps bases of reality may be a better way. Because I was doing a live stream, it was like, these, what am I going to say? They're minimal dimensions? You can't do that because you run into Planck energy and the Planck temperature. I mean, that's the obvious one. That's a ginormous number. Where it's like, well, the only time we may have gone around there was maybe start of universe as we know it. It's like, yeah, that's pretty hot. That sounds like a limit. That's a maximum. So I think of them as bases, like our base ingredients. Now, you would need to partition them and have them play together in a very particular way that will lead to the world as we know it for observers like us. God, I think I'm starting to sound a little bit more like Professor Wolfram now. I don't think that's a bad thing. Bill has a fascinating story. It's somebody asked him a question. It's like, what could you do with like a single degree of freedom or something like that? Anything useful? He's like, no, of course not. Standard can't answer. And that was one of those things. It's like he gave the answer. It's like, it was not a satisfactory answer. And it's one of those things when you say it and you're like, that's not quite right. That's not quite right. And then all of a sudden, one of the most remarkable things, and this happened with Professor Wolfram and some other folks, it's like, we initially thought this thing. It's like, you go down that path. It's like, well, it's like, oh my God, I was wrong. But then you end up discovering something even better, and you're like, oh my God, this makes more sense. And that's basically just the moral of this stream. I was conjecturing something before I was off and did some additional work and found something that seems to line up pretty well. I'm gonna stop the stream now, just because This is fun. I'm sorry. Dan! Okay. Yeah. No, I think I was listening to, I don't know, I like Brian Cox. I think he's basically the Neil deGrasse Tyson of Great Britain and stuff, and I think Dr. Tyson at one point was like, I like going to the UK because I don't get stopped as much. Because everybody knows Brian Cox over there, not Professor Tyson. So, the Tulsa Tech Conference. Ooh, I don't know. After Demysticon 2025, that was kind of a my major traveling for conferences is kind of I'm going to digitally attend Carlos Zapata's SEMF. Summer school. They're holding it in Barcelona, Spain. It's gorgeous and everything, but just it starts like right as the Wolfram Summer School is ending, and I'm like, I gotta start to recover a little bit there. So I will attend the digital ones at least for some classes. So and I like the goal. He's a good dude. Okay. Wow. I am so bad at keeping up. Higher frequency, the more energy required. Shrink the length past the Planck, and then you have infinite energy. Okay. When you say infinite energy, do you mean it needs to continually go up, or can it simply persist and that would be enough? Because that's the craziest thing is like if I take Thad's model seriously, I'm like, all right, what are the implications for this? It's going to perpetuate itself. How could that be? It's like you just take the standard notion of perpetual motion. It's like, yeah, that probably is not a thing there. And even Professor Wolfram, he's like, Yeah, you'd need to literally have a fully opaque box that you'd be able to squidge around and essentially mine, so to speak, energy from the vacuum. He's like, seeing as physical matter itself, you can't block all the wavelengths. Yeah, you're going to have an issue with that. And then, of course, just as a standard potential throwaway statement, and a throwaway statement from Stephen Wolfram can just be one of the most enlightening things in the world. He's like, I suspect you could do that with some field configuration. I'm just like, what? Huh. Because to be fair, in order to kind of justify Thad's model, you would need some form of field configuration to do that, but it's going to need to set up just right, literally Goldilocks-esque, and it's like, I think that's ultimately what we're claiming. So I think there's a lot of overlap, but the big thing is you want to be careful, especially if you have a great idea. Sometimes it's best to listen for a little while, because as soon as you jump into teaching mode, and this is something that I've heard from some of the folks here, some folks, they're very bright, but they get so passionate about something, they kind of almost do like the Tommy Boy thing, where it's like, yes, this is my sale, my precious sale, and then you just... Some of the smartest folks I know don't always have the greatest interpersonal skills and stuff, and sometimes I feel like they may do themselves a disservice. That's why I like to talk to people, so I can learn from them, get their ideas, and then start to work with ideas around those. And if somebody's like, how the heck did you do this? It's like, oh, no, I learned from this person here taught me this person here, because you give credit where credit's due, that's all. So... Okay, I'm going to leave now so I can actually grab some dinner before they shut down the cafeteria and everything. So I'll be back in probably about an hour or so, and we'll wrap up some of this, and then I need to just do my actual sessions to finish this. So, all right, everybody, you all take care. I'll catch you all on the flip side. All right, peace out, everybody.